Welcome to our third lesson in our module on matrix algebra. My name is Mr. Lippman, and today we will be adding and subtracting scalar multiples of matrices and multiplying matrices. In the past two lessons, we have looked at systems of equations and how systems define what matrices are. Now we're going to start looking more broadly at the algebra that we can do with matrices themselves. Um, and so if we want to look at the why behind our what, to build our matrix algebra toolbox, we need to study how matrices can be combined using familiar tools like addition and multiplication in new ways. These will also empower us to do many specific things with matrices that are really amazing and really necessary that we can't do just using our row operations. So to start us off, we need to remember that matrices come in many shapes and sizes of rectangles. The size of a matrix is given by its number of rows and its number of columns. So if we look here, this has 1, 2 rows and 1, 2, 3 columns. So this would be a 2 by 3 matrix. 2 by 3. Over on the right, we have 1, 2, 3 columns and 1, 2, 3 rows and 1, 2 columns. So this is a 3 by 2 matrix. So a helpful mnemonic is when giving the size of a matrix, you always want the right count. So if you have the right count, it's the R represents rows, C represents columns. So that's one way of developing that memory. An instructional coach of mine, when first talking about how she taught matrices, said that the way they remembered was referring to RC Cola. I don't even think if that drink is around anymore, but if you happen to know RC Cola, that's a fun image as well that you can stick in your mind to remember right count, rows times columns. To introduce the specific vocabulary, the size of its matrix, the size of a matrix is called its order. So all matrices of the same order have the same size. So matrices of the order 2 by 3 all have the same number of entries, the same number of rows, and the same number of columns. The numbers in each of these places are likely to differ, but their overall property, their overall shape, stays the same. And there are a lot of individual properties about matrices that can be inferred from their order, some of which we will get to in this class, some of which would require a college or even graduate school level linear algebra course to delve into. Linear algebra is an incredibly rich subject with incredibly vast potential. But what we're doing here in the context of college algebra is much more introductory. So I want to take a moment to practice stating the order of each matrix. Remember, we want the number of rows times the number of columns. So it's rows times columns. And so if we have 1 row and 2 columns, this would be a 1 by 2 matrix. Here is an excellent opportunity to pause the video, practice on the remaining 5 matrices, then unpause and come back together to watch the solutions. Of course, as I go through these, you can pause after each one to check your work more immediately. So again, pause. I'm not going to build in a lot of wait time in the video, simply because that will make the file size longer and it's inefficient. So as you need, pause, unpause, and that's that. So our second matrix has 1, 2, 3 rows and 1, 2, 3 columns. So this is a 3 by 3 matrix. We could also say that this is a square matrix. As we'll find later, square matrices have additional special properties that make them especially appealing. This next one has 3 rows and 1 column, so it's a 3 by 1 matrix. In a linear algebra class, you might also call this a column vector. Likewise, our 1 by 2, we could call a row vector. We won't need this vocabulary for the sake of college algebra, but if you are looking at this video as reference in a linear algebra class, this vocabulary is more likely to come up. Looking at the bottom left, we have another square matrix. This one is 2 by 2. We also have another one like on the last slide that is 3 by 2, and then 2 by 3. So to continue, once we have our understanding of the order of a matrix, we need to move into scalar multiples. So to first define a scalar, you maybe have heard this number or this term in a physics course or a science course, but a scalar simply represents a number. In all of the numbers we think of in a normal sense, like 1, 2, 3, pi, 7, the square root of 2, all of these numbers represent a quantity, and so they are called scalars. They are scale factors. For example, something can be twice as big as something else, or a model airplane might be 1/45th or 1/100th the size of a full-size airplane, hence where the word scale comes from. Numbers that have more than one property are generally referred to as vectors. So something like wind speed, it has an intensity, how fast the wind is traveling, and a direction. So those two pieces of information is more than just a scalar. So that's what we'd call a vector. Matrices in a broad sense of linear algebra can be considered a type of vector. If we were to make a 3-dimensional array of numbers, like a cube of numbers, we would call that a tensor, because they make mathematicians dealing with them tenser than those who can leave them behind. No, that's a fun reason, but I honestly don't know why they're called tensors. None of that is going to be required here. The important takeaway from this slide is that we can multiply a matrix by a scalar. We do that by multiplying each entry inside the matrix by the number on the outside. Think of it like distribution on steroids. So if we want to multiply this matrix by 2, we distribute this 2 into every entry in the matrix. So our new matrix would have 2 times 1, 2 times -5, 2 times 3, and finally 2 times -2. If we look at our second example, again, we are distributing the number on the outside of our matrix to the numbers on the inside. So we would have a matrix. Note that it's a 3 by 1 matrix with 15 as the first coordinate, 18 as the second coordinate, and 20, not 27, and that's not 18. Five times 6 is 30, and 5 times 9 is 45. Sometimes you get so comfortable multiplying numbers in your head that you don't pay attention to the numbers you're actually multiplying. It's a good lesson to learn in overconfidence. You can also factor out a GCF from a matrix. So notice that we can divide 10, 6, and 14 all by 2. So in a sense, by dividing everything inside by 2, we can factor out a copy of 2. So we have 2 times 5, 3, 7. And you might be wondering, why are we, if we're dividing our numbers on the inside, why do we end up with a 2 on the outside that's multiplying? So the reasoning behind this is that we're not factoring out 1/2, we're really factoring out the 2. So perhaps a more appropriate way to write this intermediate step would be to say that our matrix is really 2 times 5, 2 times 3, and 2 times 7. Once we write it in this form, it's more obvious visually how we are factoring out the 2. This only works when all of the numbers in our matrix have the same common factor. For the example on the lower right, the largest number that divides evenly into each of these is 3. So we could, to be very precise, say 12 is 3 times 4. Then we have 3 times -7 is 21. 3, we have 3 times -3 is -9. And then 3 times 5 is 15. Now we can really clearly see that 3 is a common factor in each entry. So we can factor out the 3 to have the matrix 4, -7, -3, 5. And so you may have noticed in how I read these matrices that I read matrices starting in the first row, reading all the numbers, and then the second row, reading all the numbers. So to help us make sure when we speak about a matrix, we mean the matrix that our listener thinks of, the convention that we all agree upon is when stating the entries of a matrix, we do so row by row. So 12, -21, -9, 15. If some of us said 12, -21, and some of us said 12, -9, we'd end up with different matrices when we're really trying to talk about the same thing. So conventionally, we just read like we would in English, all from left to right in the first row, left to right in the second row, and so on for the entirety of the matrix. So adding and subtracting matrices is incredibly straightforward. You can only add or subtract a matrix or two matrices if they have the same order. So if they're a different size, their sum or difference is undefined. And the strategy we use is we simply add each pair of terms. So if we have the matrices 8, 3, -4, 0, added to -1, 5, 10, 3, we would add 8 plus -1. That's our first set of numbers. Then we would have 3 plus 5, our second numbers. We would have -4 plus 10, our third number. And in our bottom right position, we would have 0 plus 3. I can put that in a square. So we're adding, essentially we're adding like terms where the likeness comes from the position in the matrix. So when we finish these computations, we would have 7, 8, 6, and 3. Likewise, we could subtract position by position, except these are different sizes. We have a 2 by 2, and we're subtracting a 2 by 3. And so the answer is undefined. And since mathematicians like efficiency, we often abbreviate undefined as UND because we tend to assume that other mathematicians looking at our work will also understand that when we write UND, we mean undefined. The reason why this doesn't work is if I try to write this out, we would have 1 minus 3, 3 minus 0. That's combining our first two numbers. But then we have this blank because there's no third column in our first matrix. So it's like a number that doesn't exist minus 1. So what's a number that doesn't exist minus 1? Well, it's another number that doesn't exist. And since that number doesn't exist, the entire matrix doesn't exist. So this is precisely where it becomes undefined. Here's a couple more examples. Again, I would encourage you to pause, work through them, and then write the solutions for yourself. Just in case you need it all on the screen before you pause. And now, assuming that you have paused and come back a minute or two later, let's actually go through these on our all together. So our new matrix would be 8 minus -1, 3 minus 5, -4 minus 10, and 0 minus 3. When we simplify our matrix, we get +9, -2, -14, and -3. Over here, we're adding so we can be a little bit more reliant upon mental math. So 1 plus 10 is 11. 3 plus -8 is -5. -4 plus -7 is -11. And -2 plus 9 would be -7. So this is where we're going to end this first video of the lesson. In our next video, we will introduce multiplying one matrix by another. Addition, subtraction, scalar multiplication, incredibly straightforward. Matrix multiplication, less so. Once you've got it, it's an easy process to follow, but getting there can feel a little bit rocky at times.